Hi everyone, welcome. My name is Grace. I'm a newly minted PhD in aerospace engineering using her background in physics to analyze gymnastics. I've been trying to think of what else I can film for gymnastics B-roll to keep things interesting, so maybe I'll try out some dance elements instead. I'm also hoping that I can find a good hill, so then I can treat it like a wedge and do tumbling up and down it. No tea this week, water instead. We're in a heat wave, and that B-roll was miserable. And I don't just mean my form. When I was younger, I was practicing 10 to 12 hours a week during competition season. Good form came a lot more naturally back then. Now it feels like I have to put more conscious thought into it. Anyways, there's one more quantity that I want to get into in linear mechanics, and that's momentum. Momentum is a measure of how difficult it is to stop or change an object's motion. Momentum depends on two things, mass and velocity. High mass and high velocity mean high momentum. You could have one or the other, or both. Like energy, momentum is a quantity that we can trace throughout a system, but unlike energy, which tells us about an object's ability to cause change, momentum tells us how much motion an object carries with it. The units of momentum are kilogram meters per second. The equation for linear momentum is P of t equals m of t times v of t, where p is momentum, m is mass, and v is velocity. And this t in parentheses means that all these terms are allowed to vary with time. This is a nice form of the equation because it combines things that we intuitively understand. Now, because these two terms are being combined, it means that high momentum doesn't just mean high mass or high velocity. A heavy object moving slowly can have the same momentum as a lighter object moving quickly. To make this more useful, let's look at how momentum changes with time. And the change in momentum is given by delta p equals p at t2 minus p at t1. If we continue to use this form in the first equation, we get where we assign the subscripts on time to both the mass terms and the velocity terms. Now, for most introductory physics problems, the mass remains constant, so we can simplify this down. Now we can divide both sides by the time interval over which the change occurs. As the time interval becomes very small, like what happens with our integral, the right side becomes acceleration. And from Newton's second law, we know that force is equal to mass times acceleration. Therefore, force is equal to the change in momentum over the change in time. This relationship tells us that force is directly related to how quickly momentum changes. Momentum is especially important when we start talking about collisions. There are two idealized types of collisions, elastic and inelastic. In an elastic collision, both momentum and kinetic energy are conserved. The classic example of this is two billiard balls striking one another and bouncing apart. In an inelastic collision, momentum is still conserved, but kinetic energy is lost. Some of it is transformed into other forms such as heat, sound, or deformation. A car crash is one example of this. Most real-world collisions fall somewhere between these two extremes. Gymnastics landings are highly inelastic. The goal is not to bounce back into the air, the goal is to land safely and absorb motion to bring the body to a stop. In contrast, rebounding from one skill to the next is closer to an elastic collision because you want continuous motion when connecting the skills. This brings us to another important quantity called impulse. Impulse is the amount of momentum transferred during a collision. You can think of it as a cumulative effect of force acting over a period of time. A large force acting briefly can produce the same impulse as a small force acting over a long time. That's why airbags, foam pits, and landing mats work. They increase the amount of time over which momentum is removed. Now we can connect this back to the energy video. We found that I absorbed roughly 280 joules upon landing my back tuck. Now that energy didn't disappear. It had to be dissipated through my muscles, tendons, joints, and the landing mat. As my velocity decreases from its value just before impact to 0, two things happen simultaneously. 1, my momentum decreases to 0, and 2, my kinetic energy decreases as well. The momentum perspective tells us how much motion must be removed from the system. The energy perspective tells us how much energy must be transformed into other forms. They're not separate processes. Energy and momentum are two different ways of describing the same event, bringing the body to a stop. When I land, I undergo an inelastic collision with the ground or landing mat. My velocity decreases to 0, which means both my momentum and kinetic energy decrease to 0 as well. My momentum immediately before landing is P1 equals mv landing. After I come to a complete stop, my momentum is 0. Therefore, the total momentum that must be removed is negative mv landing. The negative sign indicates that momentum is being removed from the system. Substituting this into our force relationship gives us. This equation highlights two ways to reduce landing forces. The first is to decrease the landing velocity. The second is to increase the amount of time over which the landing occurs. Just before landing, my momentum is approximately 2,201.37 kilogram meters per second. Depending on how the mass and velocity are distributed, this is similar to the momentum of a fast-pitch softball and a car slowly creeping forward during heavy traffic. Now, momentum itself isn't what causes injury. So as I mentioned earlier in this video and throughout my energy video, as I land, my kinetic energy goes to 0. Meanwhile, the change in momentum is what produces the forces required to stop me. From a force perspective, the critical quantity is how quickly momentum is removed. If I lock my knees and stop abruptly, the stopping time becomes very short and the force becomes much larger. If I bend through my hips, knees, and ankles, I increase the stopping time and spread the loading over a larger portion of my body. The total momentum removed is the same either way. The total energy dissipated is approximately the same either way as well. What changes is the amount of time over which those changes occur, and this in turn impacts how I experience forces while landing. Using the landing forces we estimated earlier, I'm experiencing about 2,632.94 pounds of force, or roughly 5.7 times my body weight during landing. And that's why good landing mechanics matter so much. You're not just trying to stop, you're trying to remove momentum and dissipate energy in a way that your body can safely tolerate. Momentum management is also one of the big controls problems in my area of aerospace research. When a spacecraft points a camera or rotates a solar array, they exchange momentum between different parts of the spacecraft. Over time, these reactions can build up so much momentum, the components controlling the spacecraft momentum reach their operating limits. When that happens, spacecraft have to dump the momentum and figure out a way to exchange it or transfer it to its environment. It's a different system, but the underlying physics is the same. Momentum of an isolated system is conserved. You can't just make it disappear. you have to transfer it somewhere. Anyways, thanks all for clicking and watching. I hope you found this fun, entertaining, and educational. If you liked this, please consider liking and subscribing for more post-PhD and physics of gymnastics fun. Until the next one, best regards.